Okay, and then that's might be until 1 to 8. We are talking about the ideal flow, about the flow around cylinder, about the how to derivation of velocity, and so on and so forth. So I think from this question 1.9 and so on, we try to get idea about the the properties of fluid itself, because in chapter 1, if you read the viscous fluid flow textbooks, we are focusing on so many various calculation, but in term of a little bit extension from what we do in undergraduate. So might be the equation is still the same, but we need to know how to choose the situation, how to choose the numbers, and how to be detailed in certain areas. Okay, let's say now we have we are calculating about the pressure. So according to our textbook, we could, because the pressure is might be different according to the situation. And then for example, a commonly used equation of state for water is approximately independent of temperature, because you know water is an ideal it's a common fluid, so it is not it is not easily affected by temperature. So means that you need to uh, boil water until 100 degrees Celsius to change its phase to gas. So A is the so let's say in this equation, so it's given for water A is equal to 3000 and N is almost 7, and P naught here, let's say the standard one is 1 atm, and the density for water for the standard one is let's say 998 kilogram per meter cube. And from this formula, we need to compute the pressure in atm required to double the density of water, and the bulk modulus of water at 1 atm, and the speed of sound in water at 1 atm. So the idea to double the density. So we have equation here, and we know that when we want to double the density means that P naught here is the standard value of water, and the density here is the density what we want to get. So because we want to double the density, so we put the equation here with 2 rho naught. So means that we want to have 2 times density at the end. And then we could calculate this equation. We could find that the P here, the pressure here is 381,128 atm pressure. So means that it is very, very hard to multiply the density of water. So this is just to show how hard water is. So because as you know, in our calculation, we always take water as incompressible. So mean it's not easy to compress, and it will have the density, and the density will not change. And this is the bulk modulus. So the equation here is given in your textbook. So it has negative volumetric dp pressure over d volume. So the K is the bulk modulus, and the others is showing in this note. So and then the bulk modulus also can be calculated by using this equation. So as I listed here. Okay, so and then what we do is okay, so we have this equation, and then okay, might be I make a mistake here. Why we don't have the P naught at P here? So okay, might be it's okay. So we transfer the P naught here to the right hand side here, and then we get this equation. Might be we have A times P naught here. So and then when we derive it into dP over d rho, so the value of A minus A P naught here might be can be eliminated. So okay, might be I just mistyped here. So and then we have a dP over d rho, and then we get this value here. We substitute the value, and then we get it is equal to 21.04. The different the gradient of pressure over density. And then we could substitute in this equation. So we have the value of density, and then we have the value of dP over d rho. We substitute with the equation, and then we could get the bulk modulus is 21,007. So which is equal to 2.13 times 10 by the power of 9 Pascal. So this is based on B, the bulk modulus of water at 1 atm. And then we go for the speed of sound in water at 1 atm. So this is the equation. We could get this equation from the textbooks. So we C is the speed of sound for water. So we have the bulk modulus over rho naught. So we substitute with the value that we get. And then we could get that the speed of sound in water is 1460.9 meter per second. Okay, that is about the properties. Okay, and then for 1.9, we are talking about this situation. So this is closely related to the idea of shear stress on surface, and also the we focus on this previously in rotating cylinder, rotating cone, and rotating disc. So however, for this situation, okay, we have a discussion about that. Okay, in this situation, we have an inclined plane like this. So the inclined angle is 30 degree, and we have a certain block here. So the weight of the block is 1.2 kilogram. So, and then we assume that we have a oil thickness here of 0.5 millimeter film thickness, and then this is the dimension of the block, 0.3 times 0.4 meter. So this is only the area that touching the oil. So might be the height here is not mentioned. Okay, so because the height is not will not be used in the calculation. So the question is, as shown below, 0.3 times 0.4 meter square plate slide along a 30-degree incline on which there is a film of 0.5 millimeter thick with viscosity 0.1 kilogram per meter second, assuming that the plate does not deform the oil film. So means that the oil film thickness is almost constant. And then we need to calculate the terminal sliding velocity, and also the time required for the plate to accelerate from rest to 99% of the terminal velocity. And this is the terminal sliding velocity. So the equation, I think everything I take from the textbooks. So we could say that the sliding velocity relationship is actually about the weight and sine theta. And then we have tau equal to tau times area, and also tau here, the shear stress here can be written as mu du dy times A. And so the weight sine theta here is actually because we have, I think you could imagine, okay, we have a sliding here, so we have block here. So, and then it's moved at this situation, at this direction. So, and then we need to calculate what is the normal weight. So, the normal force. So, okay, might be I draw is not so obvious. So, it might be not easy to show the difference. So, let's say we have an incline here. So, we have a block. So we have this direction, force in this direction, and then we need to have another opposite direction. However, weight is work like this. Okay, so and then if the angle here is 30 degree, then we assume this is the same angle, and then we could calculate that the weight here is actually W sine. And okay, so we have here, so we have a cos, and then the weight that contribute to the motion is W sine theta. Okay, so this is the weight sine theta. Okay, why? Because this box is moved downward like this, and then the oil film here will give box some kind of resistance. So how we calculate the resistance from this film thickness is by multiplying the tau and the area. So as we know in previous notes, okay, the idea of force is equal to tau A is actually available in this situation. So now we have force that move this box downward, and at the same time we have resistance that come from that oil, which can be written as tau times A. Okay, so this is the idea of this idea. And then to calculate the terminal velocity here, so we just assume the du here means the difference of the changes of velocity. So we assume that du is equal to v star, which is the terminal velocity. And then the dy here is actually the gap or the oil film thickness. So we just substitute the value that we have, and then we could calculate it is the terminal velocity is 0.245 meter per second. So I think you know about the idea of terminal velocity. So it's talking about when we slide down, okay, actually the box there will constant at certain velocity because it cannot move faster and faster and faster at all the time, because the weight itself will create force to the box sliding downward. So the mass of that box is actually constant, so that's why at certain point the velocity will not increase. It also occur when you have free fall. For example, you are falling from the sky, so you will not go faster and faster, because at certain time your you will have a constant velocity going down. Okay, that's the idea of terminal velocity. So, and then the second one is we need to calculate the time for the plate to accelerate from rest to 99% of the terminal velocity. So again, this is about the time here. So the relationship that we have is, okay, we need to agree that the calculation or the equation, the relation is need to mention like this, because the weight here will give more force to make sure that the box will falling down. Okay, if the weight here, weight sine theta, is totally equal to tau A, so mean that the resistance and the force downward is the same. So means that the resistance, the brake, is as same as the force that falling down, means that there is no motion, there is no movement. So we assume that the weight here is greater than the resistance of oil. So the difference of this one will give extra force from the top to the bottom. That's why the boat is sliding down. So we create the relationship of weight sine theta minus tau A, and it is equal to force. And force is normally written as m times A, which is m is the mass and A is the acceleration. So, and then So we have a 30-degree here. So we have sine theta is 0.5. We substitute the value of shear stress of tau mu du dy, and A is maintained A here. And then M mass here is actually the weight over gravity, and everybody knows this. And the acceleration here is dv over dt. Okay. Okay, so here might be there is a mistype. So the u here and the v here is actually the same one. So we are talking about the velocity. Okay, so at the second paragraph here, I just replaced the word u and v here. Okay, so and then we rearrange this one. Okay, we bring the dv over dt, okay, on to the left hand side, and then we bring everything here. So we could have, for example, weight 0.5 time with a gravity over weight. So and then we have this one time with gravity over weight like this, and then we could simplify this one so with this term. So and then we found that we have a dv dt on our left hand side, and we also have v on this right hand side. So what we need to do is we need to solve this one. Normally, if we have dv and dt, we could integrate both sides and we could solve the problems. But the problem now is we have dv dt here, and we have the value of v on the right hand side. So what we do is we just bring this v to the left hand side here, so we could rearrange the equation something like this. Okay, and then we could solve this by using the first order linear ordinary differential equation. So might be you could solve this one by because there is might be a few method to solve this one, but I'm going to use to solve this one by the idea of integration factor. So the idea is I just to create another terms that could balance all the terms. So what I do is normally in integration factor, we use the idea of e integration of the power of integration p times dx here. Okay, so what we do is we just assume that this is the p. So so the terms here, because we know that we have dv dt here, and then we have v here. So means that here is something that's very complicated at this moment. We have 5 terms inside this one. So why not we simplify this into one simple term? So we call it P. Okay, and then we write as P here. Okay, so and then P is actually is located for the integration factor at this in this equation. Okay, so and then we solve the integration factor first. So we have the exponential value e exponent value of by the power of integral p dx. So we substitute the value of p here, so which is mu a g over weight and y dt. And then if we integral this one, so we will get a new terms of t here, so it will become e by the power of mu a gt over weight y. So, okay, so and then so this is might be typing error. Okay, I will change this one. So and then we have this one dv mu a gt wi v and equal to 0.5 g, and then we multiply both sides with the integration factor. So we just multiply this one with the integration factor like this, and then we have one rules that we could simplify this term, the equation number 1. So the rule is this one. So if we have d dx for e by the power of e squared times y, so we could simplify it as this one. So and then if you see this one, okay, we will see what we have here in equation number 1, and we compare with the basic rules here, we could say that we could simplify the term here as this one. Okay. Okay, I hope you could snap this screen. And then suddenly the integration of both of this one, because the terms here is quite simple. We have one term at the left and one term at the right here. So to get the value of eliminate the value of d dt here, what we need to do is we integrate all of them. So the integration of d something here will give its own term. So means that the integration of this one will give v times e by the power of this one, and the integration of this one will give you the value of t. Okay, so the integration of dt here is actually involved, is related to the power of this one. So because the power here has the t, so we could it will become, so this is the terms, and then we need to integral the power here, and then we times it here, so we have this one, and then we times the we plus the coefficient here. So and then to simplify this one, so we divide both with this term again, and then we could get that the v here, the v is 0.5 wy over mu a plus c times e by the power of this one. So and then c is the constant, and then we need to determine the value of c. So and then our boundary condition is when t is equal to 0, the v is equal to 0. So means that at the very beginning, when the t is 0, there are no velocity. So we substitute this value, we could get that everything is 0. So the v is 0 when the t is 0. So we could get the value of c. So we could, the c here can be written as minus 0.5 wy over mu a. So and then we substitute with the original equation. So we could finally say that the v is actually this equation. And from part A, so we know that the w sine theta is equal to mu. This is the idea of mu du dy over a. Okay, because tau is equal to a and tau is equal to mu du dy, and we know that it is the u is the terminal velocity and y is the gap of the film thickness. And then if we rearrange this equation, we could get this value. You could get this relation. So and then we by using equation number 5 and number 4, we could substitute the value the value of v. So and then we could say that okay. So okay, so I'm lost here. Okay, so v star. Okay, I'm sorry. Okay, so so you compare this one, this equation with this equation. Okay, with this one, and then I think we could have this equation, and then finally we substitute the value of v equals 0.99 v star, because we want it's 99% of v star, and t equal t star because the time for the terminal velocity So we substitute with the in equation 6 here. So and then we rearrange. Okay, we could solve the value. We could solve the equation here. And finally, we could calculate the value of T star. It's actually this equation. We substitute all the values and then we get the T star is equal to 0.23025 seconds.